All right, welcome. Today, we're jumping past the textbook stuff to get our hands on a seriously practical tool for your data analysis toolkit, the Wilcoxon signed rank test. Look, if you've ever had to pull real insights from real-world data, the messy, skewed kind that just refuses to fit into a neat little bell curve, then you know that having the right tool is absolutely critical. Use the wrong one, and your recommendations could be completely off. So in this explainer, we're going to break down what this test is, and maybe more importantly, why and when you need to pull it out to make sure your conclusions are rock solid. Let's get into it. We're going to approach this just like a consulting project, using a really clean MEIS framework, so we cover everything we need to with no overlap. First, we'll nail down the core problem we're trying to solve. Then, we'll introduce our tool, the Wilcoxon test. After that, we'll go through its operating manual, the assumptions you can't ignore. Then we'll get our hands dirty with a step-by-step data walkthrough. And finally, we'll really sharpen our skills by mastering the tricky parts of making that final call. It's a logical path from problem to a bulletproof solution.
So let's kick things off with Section 1, the real-world data problem. Before we learn how to use any tool, we have to be crystal clear on what it's for, right? So why do we even need something like the Wilcoxon test? Well, it all starts when your data does what data so often does. It decides not to cooperate. And here it is. This is the big question every analyst hits sooner or later. You've got your data, you're all set to run a standard t-test, but then you do your homework. You plot it out and, instead of that nice, pretty bell curve, you've got something skewed or with really heavy tails or a couple of wild outliers. This is a huge fork in the road. If you just push ahead with a test that assumes normality, you could completely tank your analysis and end up making some really bad calls. That fork in the road leads us to two totally different worlds of hypothesis testing. On one side, you've got your parametric tests, like the famous t-test. They're powerful, for sure, but they have strict rules. The biggest one is that your data has to follow a specific pattern, usually the normal distribution. On the other side, you have the non-parametric tests. Think of these as the rugged, all-terrain vehicles of statistics. They don't make those assumptions about your data's shape, which makes them way more flexible and tough enough to handle the messy, unpredictable data we usually find out in the wild. So, that brings us to Section 2. Now that we've defined the problem, that non-normal data, let's introduce the specific tool we're here to talk about. This is your go-to when a t-test just isn't the right move. So what is this thing exactly? Well, the Wilcoxon signed rank test is built to answer one key question. Is the median of my data different from some specific value I have in mind? Now, notice that key word, median, not mean. And why is that? Well, think about it. One crazy outlier can yank the mean way over, giving you a totally misleading picture of the center. But the median? That's just the middle value. It's tough. It's resistant to those outliers, which makes it a much more honest measure of the center when your data's all over the place. And this isn't some new experimental technique. It's got a solid history. It was actually developed way back in 1945 by a chemist named Frank Wilcoxon who needed practical tools to analyze real lab data that didn't fit those perfect theoretical models. It was born out of pure necessity, not just academic theory, which is why it's so useful. This slide really shows you where the Wilcoxon sits in your toolkit. The default path is the t-test for clean, normally distributed data. But the second you see that your data breaks that rule, you take the non-parametric off-road path with the Wilcoxon. It's also a huge upgrade over its simpler cousin, the sign test. See, the sign test only cares if a data point is above or below the median, just a plus or a minus. The Wilcoxon is smarter. It looks at the size of those differences, too. It gives more weight to points that are further away, which means it uses more of the information in your data, giving it more power to find a real effect if there's one to be found. Okay, on to Section 3. Before you use any powerful tool, you gotta read the instruction manual, right? For statistical tests, that means understanding its core assumptions and knowing how to frame your questions. These are the absolute rules of the road. Every test has ground rules, and for the Wilcoxon, these are non-negotiable. So let's quickly walk through them. First, your data should be continuous. Second, and this is a really subtle but important one we're going to come back to, the distribution of the differences around the median needs to be symmetric. This is key to the whole ranking system being fair. Third, each data point has to be independent. And fourth, your measurement scale needs to be at least an interval scale, so the distance between numbers actually means something. Okay, next up, we have to translate our business question into the language of statistics. This always starts with the null hypothesis, H0. That's the default, the nothing's going on here assumption.
The alternative hypothesis, H1, is what you're actually trying to prove. As you can see, if you want to know if the median is greater than some value, that's a right-tail test. If you're testing if it's less than, that's a left-tail test. And if you just want to know if it's different, one way or the other, you use a two-tail test. It all depends on the question you're asking.
And that brings us to section 4. This is where the rubber finally meets the road. We are done with the abstract theory. It's time to roll up our sleeves and walk through a full data example step by step. The procedure itself is actually pretty logical. Let's just follow the steps here. First, for every data point, you find the difference between it and the median you're testing. Easy enough. Second, if any point lands exactly on the median, you just toss it out. Third, and this is the heart of the test, you rank the absolute differences, ignoring the signs for a minute from smallest to biggest. Fourth, now you bring the signs back. You add up all the ranks that came from positive differences, and you add up all the ranks from the negative ones. Fifth, your test statistic, which we call W, is simply the smaller of those two sums. And finally, you take your W and compare it to a critical value from a statistics table to make your final call.
Okay, let's make this real. Here's our case study. We're looking at a law college, and the question is, do we have evidence that the median student mark is actually greater than 67? So we set up our hypotheses. The null, H0, is the status quo. The median is 67 or less. The alternative, H1, is what we're looking for evidence for, that the median is in fact greater than 67. This is a classic right-tailed test.
Now for the fun part, the calculation. Let's just walk through this table. First column, you see the actual student marks. Second column, we've calculated the difference from our target median of 67. So a 71 is plus 4, but that 40 is way down at negative 27. Third column, we just ignore the plus or minus signs and look at the raw distance. And finally, the fourth column is where we rank those absolute distances. The smallest difference, 2, gets rank 1. The next smallest, 3, gets rank 2. And we go all the way up to the biggest difference, 27, which gets the top rank of 10. That's it. That's the core of the whole thing. All right, so now we take all those ranks we just figured out and we sort them. We add up the ranks that came from the positive differences, and that gives us a W plus of 40. Then we add up the ranks from the negative differences, giving us a W minus of 15. Now here's the key rule. Your final test statistic, W, is always the smaller of those two numbers. So in our case, our W is 15. Okay, so we have our test statistic, W equals 15. But what does that mean? Well, it means nothing on its own. We need a benchmark to compare it to. So we go to a standard Wilcoxon test table, and for our sample size and significance level, we find the critical value is 11. Think of this as our hurdle. This is the number we need to beat.
And here we go. This is the moment of truth. We put our test statistic, 15, up against the critical value, 11. Now listen closely, because this is where it can feel a little backwards. With the Wilcoxon test, a small w is what you're looking for. The rule is you only reject the null hypothesis if your w is less than or equal to the critical value. Since our w of 15 is obviously bigger than 11, we haven't cleared the bar, so we fail to reject the null hypothesis. The bottom line? Based on this data, we don't have enough evidence to say the median mark is greater than 67.
But we're not going to stop there. This last section is all about getting to that next level of mastery. This is where we go beyond just crunching the numbers and really tackle the common points of confusion that pop up when you use these tools for real, by looking at some great feedback from the source material. And this brings us to an absolutely perfect question from Kamru Zaman Asif. He says, hey, our test statistic is bigger than the critical value, so shouldn't we reject the null? This question gets right to the heart of the single most confusing part of the Wilcoxon test. For anyone used to other tests like a t-test, this feels totally wrong. Okay, let's clear this up once and for all. For a lot of other tests, the rule is big number means reject. With Wilcoxon, it's the exact opposite. And here's why. Our test statistic, W, is the sum of the ranks for the weaker side of the evidence. A really, really small W means that almost all the weight, all the big ranks, are piled up on the other side. That huge imbalance is what gives you strong evidence against the null. So the rule is simple and absolute. Reject H0 only if your W is less than or equal to the critical value. Our W of 15 just isn't small enough, so the decision to fail to reject was absolutely correct. Now check out this next piece of feedback. This is a brilliant, expert-level observation from a user named Steven. He points out that the data itself doesn't look very symmetrical. which, as he correctly says, should violate one of our core assumptions. This gets to the very heart of what it means to apply statistics in the real world. And this really highlights the art of being a good analyst. Stephen is 100% right. The symmetry assumption is critical, and his instinct to visually check the data is exactly what you should do. The original authors even point out that with a tiny sample size of 10, perfect symmetry is almost impossible to find. Real data is messy, so the big takeaway here is this. Don't just be a robot who runs tests. Be a detective. Always, always check your assumptions first, because the results are only as good as the care you took in setting up the test. And that leaves us with one final, bigger picture thought. We've just spent all this time learning the rules, the assumptions, the whole procedure. But as Stephen's fantastic comment just showed us, sometimes the most powerful insight doesn't come from the test result itself, but from realizing that your data refuses to play by the rules. So I'll leave you with this to chew on. Now that you know the rules, when might the act of finding a broken assumption actually be a more valuable discovery than whatever the test was going to tell you in the first place?